Okay, review of Unit 2 on functions. Start out with a definition of a relation. A relation is a set of ordered pairs. A relation may be expressed either by listing the ordered pairs or with a formula. Here are some examples. Relation A, a set of three ordered pairs, 1, 4, -1, 4, and 2, 5. Relation B and C have an infinite number of ordered pairs, and they're defined by a formula. Relation B is a set of ordered pairs xy. It's an element of r squared, such that x squared plus y squared equals 25. So you may remember from Unit 1 that this is the equation for a circle of radius 5 centered at the origin. So there's an infinite number of points on the circle. Relation C is the set of ordered pairs xy, such that y minus 1 is equal to the square root of x minus 2. This is a piece of a parabola. I like to call it a semi-parabola. Okay, so those are examples of relations. A function is a special relation in which each first coordinate appears only once. So A is a function because we have, if you look at the first coordinates, we have 1, -1, and 2. Each one only appears once. So A is a function. B is not a function because if you solve for y, you get two formulas for y, namely y is equal to either the positive square root of 25 minus x squared or the negative square root of 25 minus x squared. So you have two y values for the same x value. So relation B is not a function. Relation C is a function because if you solve for y, you get only one formula for y, and that's y is equal to the square root of x minus 2 plus 1. If you graph a relation, you can also tell whether it's a function from the graph. If any vertical line touches in more than one point, then the relation is not a function. For example, a circle, relation B, if you remember relation B, it's the equation for a circle, and I'll just draw a coordinate system here. But there's certain places where if you draw a vertical line, it'll touch the circle in more than one spot. So you can actually tell from the graph. Also, and that's called the vertical line test. In order to emphasize that relation C is a function, we can write with the notation f parentheses x. It's read f of x equal square root of x minus 2 plus 1. So instead of y equals, we'll have f of x equals. And it looks like multiplication, but in this context it is not necessarily multiplication. It's just emphasizing that f is a function of x, or y is a function of x. So this is function notation. Okay, so go over some more terminology here. The domain of a relation is a set of possible first coordinates. The range is the set of possible second coordinates. In this class we'll assume functions have real values, so that first of all, maybe I'll do the domain of relation A. Domain of relation A, the domain would be just the values 1, -1, and 2. That's the domain. The range would be the values 4, 4, and 5. So actually the range only has two values. But anyway, for relation C, which is also a function, we can determine the domain as follows. Because we're in this class we're working with real valued functions, we're assuming the square root of x minus 2 is real, and that means what's underneath the square root has to be greater than or equal to 0. If you recall, the square root of a negative number is an imaginary number. It's not a real number, but we're mostly working with the real numbers in this class here. So that means that x minus 2 has to be greater than or equal to 0, which means that x is greater than or equal to 2. So the domain is a set of x such that x is greater than or equal to 2. Or in interval notation, it's a square bracket 2 and then a round bracket at infinity. It means the domain goes from 2 out to infinity. It includes 2, but that does not include infinity. And we can also make a similar argument for the range. So the square root of, we're assuming the function is real value. That means square root of x minus 2 is real, and that means it has to be greater than or equal to 0, because this symbol here means the positive square root. And if we add 1 to it, it means it has to be greater than or equal to 1. So this is, the left side here is actually the formula for f of x. So that means that f of x has to be greater than or equal to 1. So the outputs, f of x would be the outputs from the function. That means, so the range would be the set of y such that y greater than or equal to 1. Or in interval notation, the range is square bracket at 1, comma, infinity. So it goes from 1 to infinity. It includes 1 because of the square bracket. Okay, so that's domain and range. Also, we have the notion of increasing or decreasing. A function is increasing on an interval if on that interval, if x2 is bigger than x1, that means f of x2 is greater than f of x1. And in fact, the function f of x equals square root of x minus 2 plus 1 is in fact increasing on the entire domain. Because x bigger than x2 bigger than x1, it means if you subtract 2, it's still true that x2 minus 2 is bigger than x1 minus 2. If you take the square roots, the inequality still holds. And if you add 1 to both sides, the inequality still holds. So that means that f of x2 has to be bigger than f of x1. You can, if you graph it, you can tell from the graph too. The graph is, this is a semi-parabola, so the graph looks something like something like this is the graph. It's a piece of a parabola, semi-parabola. Okay, so so you can use the graph to determine intervals of increase. And we also have the notion of decreasing. Basically, the increase and decrease is it's an extension of the idea of slope. So with straight lines, we have the slope. If you have a positive slope, it's increasing as you go left to right. So this is sort of an extension of that idea. And in calculus, you actually compute. If you go on to calculus, you actually compute the slope. You can compute the slope at each point on the graph. You write down the formula for the slope of different graphs, different functions. Okay, so decreasing, if x2 is bigger than x1, and f of x2 is less than f of x1, then the function is decreasing on an interval. And the function f of x equal square root of x minus 2 is not decreasing anywhere, so it's strictly increasing. It's on its entire domain. Another notation is 1-to-1. A function is 1-to-1, also called invertible, if x is also a function of y. So if function of y equal f of x is called 1-to-1 or invertible if x is also a function of y. And that function is called the inverse function. So let's see if we can find an inverse function for f of x equals square root of x minus 2 plus 1. So the procedure is, the first step, instead of f of x equal, we want to write y equals. So step 1, y equals square root of x minus 2 plus 1. And then step 2, we want to switch x and y. So we want to write x as a function of y here. And then solve for y. Okay, so we can subtract 1 from both sides. So we'll have x minus 1 equals y minus 2. and then we can square both sides. So if we square both sides, the square and the square root cancel, and we'll have x minus 1 squared is equal to y minus 2. By the way, this is the original formula. We have x greater than or equal to 2, y greater than or equal to 1. And when we switch the x and the y, we also switch the domain and range. So this is going to be x is greater than or equal to 1, y greater than or equal to 2. So this formula here, so we're mainly interested in the restriction on the x value. So the x has to be greater than or equal to 1. We can add 2 to both sides, and we get x minus 1 squared plus 2 is equal to y. Or we can, usually it's traditional to put whatever you're solving for on the left. So we can write y equals x minus 1 quantity squared plus 2. And then step 3, and because we only have one formula for y here, this is actually a function. The inverse is actually a function. So we can, instead of y equals, we'll write f inverse of f equals, to emphasize that this is the inverse of the original function. And this formula only applies for x greater than or equal to 1. If we don't include that, then what we have here is actually not a function, not an invertible function. I mean, not a one-to-one function. But okay, so the original function was invertible. This is the inverse, and the inverse goes both ways. So when you have an inverse function, the inverse function itself is 1-to-1, and its inverse is the original function. So so these are inverses of each other. These two functions are inverses of each other. Yeah, just a couple of comments. This notation, the same notation is used to indicate the multiplicative inverse, but this is, in this context, it means the function inverse. So the inverse function could include a multiplicative inverse. It also could include an additive inverse, inverse of square roots, reverse order of operations. So it's not simply a multiplicative inverse, but it's the same notation. And for this particular one, we have the inverse of square rooting. We have a square here, and we have a square. We start with a square root, so that the reverse of square rooting is squaring, and we also have a multiplicative inverse. We have, an additive inverse. We actually have two additive inverses. We have a minus 2 here, and a plus 2 here, and we have a plus 1 in the original function, and we have a minus 1 in the new function. And we also have the reverse order of operations. So the original function, we start out by subtracting 2, then taking the square root, following the order of operations, then adding 1. So the first thing we do is subtract 2. The last thing we do is add 1. For the inverse function, the first thing that we do is subtract 1, and the last thing we do is add 2. So it's a reverse order of operations. We have two additive inverses, and we also have the squaring, which is the inverse of square rooting. This particular one doesn't not have a multiplicative inverse, but the inverse function could include a multiplicative inverse also. Anyway, this notation is, in this context, it means a function inverse, which is a broader concept than multiplicative inverse. Okay. So the function this function here is a transformation of a quote-unquote toolkit function. I mean, this toolkit function refers to functions that are fairly common and can be used to inform us about the graphs of other functions. One of the toolkit functions is square root of x. That's a semi-parabola. The graph of a square root of x the vertex of the parabola is at 0, 0 as a semi-parabola. The full parabola would have a piece down here, but this is a semi-parabola. And so this here we're subtracting 2 from the x-coordinate, which moves the graph to 2 places to the right, and then we're adding 1 to the y-coordinate, which shifts the graph up 1. So whatever you do to the x-coordinate kind of has the opposite effect of what you might think. Subtracting 2, you might think you move 2 to the left, but if it's inside parentheses or inside a square root, it has the opposite effect of what it looks like. So this is a shift of 2 to the right and up 1. So the new parabola is 2 to the right, up 1, maybe goes something like this. That's the new parabola. So there's other toolkit functions that are useful to sort of familiarize yourself with. If you're making a graph, you can always do point plotting, but sometimes it helps to know what the general shape is before you do the point plotting. So the square root is a semi-parabola. The square root of 1 minus x squared is a semicircle. So this one is our semi-parabola here, centered at 0, 0, or with the vertex at 0, 0 rather. This one here is a semicircle, centered at 0, 0, radius 1. The graph of the power function, if you have an even power, it could look like a parabola. Even powers, something like this. With the higher even powers, the parabola kind of flattens out. With an odd power, if you have x to an odd power, it tends to look like pieces of 2 parabolas pasted, semi-parabolas pasted together. It looks a little bit like that. Absolute value is a V-shaped graph. And 1 over x, the reciprocal function, is a hyperbola with the axes, x and y axes are actually the asymptotes of the hyperbola. That's the hyperbolas that we were working with earlier in the course mostly were not functions, but this one is a function. And the domain would be all real numbers except for 0. If x is 0, then it's undefined, and that's actually where one of the asymptotes is, and the range is the same. The y value cannot be 0. The greatest integer function, that's a staircase type function, and it looks something like this. Keep losing my. So the greatest integer function actually, there's an application to postal rates. When the postal rates, if you have less than an ounce, you're mailing first class mail. If you're mailing less than an ounce, then you pay a certain amount, maybe something like 50 cents or something. And then as soon as you hit full ounce, 1 ounce, then you add another 20, something like 20 cents. So so the price jumps up, and then if you add a 1/3 ounce, then the price jumps up again. So there's so it's kind of a staircase type of pattern. That's so the postal rate would be a transformation of the greatest integer function. So the greatest integer function, just the generic function would be the greatest integer less than or equal to x. So for example, the greatest integer less than or equal to 3.7 would be 3, or the greatest integer less than or equal to 3.9 would be 3. But as soon as you get to 4, the greatest integer less than or equal to 4, that's going to be then the value jumps up to 4. So the postal rates would be a transformation of the sort of the generic greatest integer function. So anyway, these functions here are, it's good to sort of be familiar with the shapes of these functions. They can help you to recognize the graphs of a variety of functions. Okay, so let's go over some examples. I sort of, this is kind of example 0, I guess, because I was using that to sort of illuminate the definitions. But let's go over some additional examples. This is example 1. The height in feet of a rocket at time t seconds after fuel runs out is a function of time. H of t minus 16t squared plus 48t plus 28. Part A, we want to know how long it takes the rocket to hit the ground. So when the rocket hits the ground, the height is 0. So you want to solve h of t equals 0. So so we can factor out -4 here. There's a common factor of -4. -4, and then divide each term by -4. We have 4t squared plus 12t plus 7 equals 0. Okay, so let's see if we can factor that. Let's try 2t and 2t. If that doesn't work, we'll try 4t and 1t. But we need the first two terms have to multiply to 4t squared. So I'm going to start out with 2t and 2t. And then we need two numbers to multiply to 7. There's not a lot of choices there. Basically either a positive 1 times positive 7 or a negative 1 times negative 7. So I'll try, this is okay, so -4. You know what? I got the signs wrong here. -4. This is -12, and this is -7 here. Okay. Okay. So we want either a positive 1 times a negative 7, or negative 1 times a positive 7. So let's apply +1 and -7, and see if we get the middle term. So the outer product is -7 times 12 times 2 is -14, and then the inner product 1 times 2 is +2, and that gives us our middle term, with -12. So that works. So so that means, well, -4 equals 0, or 2t plus 1 equals 0, or 2t minus 7 equals 0. So that's the zero product rule. So in order for this product to be 0, at least one of these has to be 0. So we knew -4 is not 0, so we can scratch that possibility out. And if we solve the other ones for t, subtract 1 from both sides, we have 2t equals -1, and then divide by 2, we get t equals -1/2, so that's going back in time. If we add 7 to both sides, we get 2t equals 7 divided by 2, and we get t equals 7/2 seconds. So that's 3.5 seconds. So that's how long it takes to hit the ground. The other solution is going back in time. Okay, so this is the one we want. We'll use this other piece of information also, but this is the answer to part A. Okay, so what time does the rocket reach its maximum height? So it's going to be, when you see a t squared and some other terms of lower powers, the graph is going to be a parabola. Parabolas are symmetric. Now the graph of a parabola, this comes back to transformation of functions again, but the graph is going to look something like this. And we have one t-intercept here and one over here, and the maximum height is halfway between. Because of the symmetry of the parabola, maximum height is going to be halfway in between those two t-intercepts. So if we just take the average of the two t-intercepts, -1/2 plus 7/2 divided by 2, that's 6/2 divided by 2, be 6/4, or let's reduce it to 3/2, or 1.5 seconds. So the time of the rocket reaches the maximum height is about 1.5 seconds. And then part C, what is the maximum height? Well, we just have to plug in 3/2 into this formula here. So this will be h of 3/2 will be -16 times 3/2 squared plus 48 times 3/2 plus 28. So this is going to be -16 times 9/4. 2 into 48 goes 24. 24 times 3 is 72. 4 into 16 goes 4 times. 4 times 9 is 36. So this will be -36 plus 72 plus 28. And that comes out to be 64 feet. Okay, so the maximum height is 64 feet. So the rocket goes up for a while. After the fuel runs out, the rocket goes up for a while from its own momentum, but eventually gravity slows it down, and then eventually gravity pulls it down. We could also, another way of doing this is if we use the methods from earlier in the course, we could use those methods to write the equation in standard form for identifying the vertex. There's a couple of forms. This form here is useful for if you're mainly interested in the intercepts. This other form is useful for identifying the vertex. So if you put it in this form here, use the method of completing the square, the vertex, the t coordinate is going to be 3/2, and the h coordinate is going to be 64 feet. This should be, say, completing here. Method of completing the square. Okay, so you could use that method also. The height of the rocket when the fuel runs out, that would be the height at time 0, h of 0. And the original formula is actually probably the easiest one to use for h of 0. Use this formula here, just replace t by 0, and get minus 16 times 0 squared plus 48 times 0 plus 28, which would be 28 feet. So at the time the fuel runs out, the rocket is 28 feet in the air. And then we can sketch the graph. We actually have some information we need now to sketch the graph. We know the intercepts, -1/2, 0. The height is 0 at time -1/2. At time 0, the height is 28 feet. At time 3/2, or 1.5, it reaches the maximum height of 64 feet. And at time 7/2, or 3.5, it's back on the ground. We can sketch the graph here. So this would be 1, 2, 3, go up to 4. This one I have to go up to, also go up to at least 64, but okay, so we have height at we have a 0. So this is 1/2, should be 1/2. 1/2, and then 0.28, that's about right here, and 1.5, 64, about right here, and 3.5, 0. Okay, so this is a piece of a parabola here, and the full parabola actually keeps on going, but once the rocket hits the ground, it's going to be it's not going to go very far into the ground, because the ground offers a lot more resistance than the air does, and also before the fuel runs out, the speed of the rocket, the velocity of the rocket is actually increasing because the fuel is burning. So the formula really only applies from time 0 until time 3.5 seconds. So I put that part of the graph in with a solid curve, and then I put dots to indicate the rest of the parabola, a dotted curve there. So the domain, because the formula only makes sense from 0 to 7/2, the domain would be the set of real numbers t, such that t is between 0 and 7/2. Or in interval notation, you have square brackets, 0, 7/2. The square brackets indicate that the two endpoints are included. Likewise, the range is also restricted here. It's the height of the rocket is between 0 and 64. The parabola goes below 0, but the rocket does not. The formula no longer applies once the rocket hits the ground. So the range would be the set of h, such that h is between 0 and 64, or in interval notation 0, 64. Again, with the square brackets to indicate the endpoints are not included. We could also ask on what open intervals the rocket is increasing. The height of the rocket is increasing, and it's apparent from the graph. From time 0 to time 3/2, right? That's when the height is increasing. You have a positive slope there, and then it's would be decreasing from time 3/2 to time 7/2. That's when it hits the ground. The average velocity of the rocket from time 0 to 7/2 okay, so that's that would be the slope of the secant line. So average velocity, geometrically, it's the slope of the line that touches the graph and just 2 points there. So it's the slope of the secant line. So the slope. So we have 2 points, and we can compute the slope of the line through those 2 points. So that's going to be the difference of the y values is y2 minus y1 over x2 minus x1. Or in terms of h and t, it's going to be h of 7/2 minus h of 0 over 7/2 minus 0. So this h of 7/2, we already computed that. That's 0, right? And h of 0 is 28. So it's going to be 0 minus 28 divided by 7/2. The way you divide by fraction, flip and change it to multiplication. So it's negative 28 times 2 over 7. 7 to 28 goes 4. Negative 4 times 2 would be negative 8 feet per second. So on the average, in fact, from the picture, it looks like the slope is negative, right? So on the average, the rocket is going down, so that it's a negative velocity on the average. It's going up, and then later it's going down further than it actually went up. Average velocity from time 3/2 to 7/2. So that's times 3/2. That would be at the maximum height. That would be again, it's the slope of the secant line, but it'll be a different secant line here. It looks like it's a steeper line. We expect it to be a steeper slope. So average velocity is 3/2 is 7/2. So it's h of 7/2 minus h of 3/2 over 7/2 minus 3/2. So h of 7/2 is 0. H of 3/2 is 64. 7/2 minus 3/2 is 4/2, which is 2. So h of 7/2 is 0. H of 3/2 is 64. We already computed. So this is going to be negative 32 feet per second. So and you can. So it's speeding up actually. The gravity is causing it to go down, but the speed is increasing. It has a negative slope, and it's a larger in absolute value. So it's the speed is increasing, and we can also use the difference quotient to determine the instantaneous velocity. So, as the rocket gets closer and closer to the ground, it's speeding up. So the instantaneous velocity would be the slope of the line that just touches. So the secant lines touch in one point, but the tangent line just touches at the one point. So we want the slope of the tangent line, and we can use the difference quotient to compute that. So the difference quotient, there's a formula that we were working with. It's based on the the same formula of the slope we were working with before, but it looks a little bit different. So it's going to be h of t plus h, little h. We'll have a capital H and a little h, minus h of t over h. So that's the difference quotient. So h of t plus h. So this is going to be minus 16 t plus h quantity squared maybe I'll do that on a different line. I think I'm going to run out of space here. I had to do a different sheet of paper here. 16 t plus h squared plus 48 times the quantity t plus h plus 28. So that's h of t plus h. So I just, in the formula for h of t, I'm just replacing t by t plus h. And then when I subtract h of t, so subtract means you want to change the sign, so it'll be plus 16t squared minus 48t minus 28, and the whole thing is over h. This is h of t plus h minus ht. That's like y2 minus y1, and if on the bottom we'll have t plus h minus t, which is like x2 minus x1, but the t's cancel and just leave us with h. Okay, so the 28 minus 28 will cancel. So now we won't take up so much space here. I'll expand this piece here. This is t plus h times t plus h. We'll give t squared plus 2th plus h squared. I can distribute the 48, so plus 48t plus 48h plus 16t squared minus 48t all over h. Okay, so this is 48t. I left off the t here. Okay, so the 48t's will cancel. And we can distribute the minus 16. So this will be minus 16t squared minus 32th minus 16h squared plus 48h plus 16t squared over h. Okay, so the 16t squared will cancel. And the other terms we can just divide by h, divide each of these by h. So we'll give, because all the three remaining terms all have an h in them. So we have minus 32t minus 16h plus 48. Okay, so that's the difference quotient. They don't. So that's actually they gave you the difference quotient in the book, but they don't really tell you how it's used. And I think it's good to know. I think you're more likely to remember something if a formula has some meaning to it. And so I'm going to take it a little bit further. We want to replace this h here with 0. So, you know, as these 2 points get closer and closer together, h is going to get closer and closer to 0, and we want to take the limit. And to get the velocity, so as a function of time. So v of t is going to be the limit as h goes to 0 of minus 32t minus 16h plus 48. So if h goes to 0, that drops out, and we're just left with minus 32t plus 48. So that's the instantaneous velocity. And then, so the velocity as the rocket hits the ground, we would do v of 7/2, replace minus 32 by 7/2, and that comes out to be a negative 64 feet per second. So, so the velocity as it hits the ground. So you can see the velocity is the absolute value of the velocity is increasing as the rocket it gets closer and closer to the ground. Initially, we had a rather gradual slope here, downward slope, and then as we get closer, the slopes get bigger, and we had an average velocity of negative 8 feet per second, then negative 32 feet per second, but as it's hitting the ground, it's negative 64 feet per second. Okay, so that's an example. Let's go over another example. I think with the first example with the rocket, I didn't really touch on all the topics of the course. It's good to do some applications. I like that example because it's I think it helps to know how the stuff is used. In the text, they'll have more generic functions that don't have a particular context. So let's this second example, we'll have two functions. F of x is 1 over x minus 3. G of x is x over x plus 2. By the way, these are both of these are hyperbolas. They're transformations of the function 1 over x, which is a hyperbola. The domain, with fractions, the only thing to be concerned about with the domain is the denominator. If x is 3, you'll have 0 in the denominator. You can't divide by 0, or at least dividing by 0 doesn't give you a real number. So the domain in set builder notation, the domain is set of x such that x is not equal to 3. Or in interval notation, it's minus infinity to 3 union 3 to infinity. So it's anything but 3. And the round brackets indicate that 3 is not included. Infinity is also not included. The domain of g of x can be anything except for negative 2. So it's in set builder notation, set of x such that x is not equal to negative 2, or in interval notation, minus infinity comma minus 2 union minus 2 comma infinity. So now with this example we have two functions. There's things we can do with two functions that we can't do with just one function. One thing is that we can do with two functions is we can compose the two functions. We can okay, so let's do the composition f of g of x. This is also written with this notation here. That notation is also used. So in the formula for f of x, wherever you see an x, you want to put a g of x. So this is the output for g becomes the input for f. So this is going f of g of x is going to be 1 over g of x minus 3. You're just replacing x by g of x in this formula here. And now we can substitute in the formula for g of x. G of x is x over x plus 2. So this is going to be 1 over x plus 2 minus 3. And now we have a fraction within a fraction. So that's basically the formula for the composition, but usually it's nice to simplify things. So the inside fraction has denominator x plus 2. That's what I'm going to multiply each term by x plus 2 to try to simplify this fraction here. So we'll have 1 on the top, we'll have 1 times x plus 2. On the bottom we'll have x over x plus 2 times x plus 2. And we'll have minus 3 times x plus 2. So so here the x plus 2's will cancel on the bottom left, and we're just left with an x there. We can distribute the 1. So on the top we'll have x plus 2. 1 times x is x. 1.2 is 2. Copy the x on the bottom left. Distribute the minus 3. We'll have minus 3x minus 6. And then we can combine like terms. So we have x plus 2 would be x minus 3x is minus 2x minus 6. Okay. Okay. Sometimes it's helpful to factor the denominator. You could leave it like I had it, or if you factor the negative 2, sometimes it's useful to do that. 2 times the quantity f plus 3. Okay, so that's the combined function, and it's also important here to state the domain. So x cannot be negative 2, because if x is negative 2, we can't get past this step here where we had a fraction within a fraction. So x is not equal to negative 2. And also, in the final answer, x cannot be negative 3, because if x is negative 3, then this denominator here will be 0 in the final answer. So x is not equal to negative 3. So we have two numbers that x cannot be for this function. Okay. We could also, this function we had g as an inside function. We could also take g as the outside function and compute g of f of x. And this one, in the formula for g now, wherever we see an x, you want to put an f of x. So we'll have, this will be f of x over f of x plus 2. So in the formula for g, just replace x by f of x. And then for each f of x, wherever we see an f of x, we want to write 1 over x minus 3. So this is going to be 1 over x minus 3 all over 1 over x minus 3 plus 2. So again, we have a fraction within the fraction, so it would be nice to simplify this. So we want to use the denominator of the inside fraction to simplify it. Multiply each term by x minus 3. So it would be 1 over x minus 3 times x minus 3 over 1 over x minus 3 times x minus 3 plus 2 times x minus 3. Okay, so the x minus 3's will cancel the top and also the bottom left. And we can distribute the 2. And so this will give us 1 over 1 plus 2x minus 6. 1 minus 6 is negative 5. So this is going to be 1 over 2x minus 5. Okay, so again, it's important here to restrict the, mention the domain restrictions here. So x cannot be 5 halves on the final step here. If x is 5 halves, we'll have denominator 0. And also, we can't get past this first step here if x is 3. So x is not equal to 5 halves, x is not equal to 3. Okay, we can also compose a function with itself. F of x. So in the formula for f of x, wherever you see an x, you put an f of x. So this is 1 over f of x minus 3. And then we want to replace f of x by the its formula 1 over x minus 3. So this is 1 over x minus 3 minus 3. Okay, so again we have a fraction within a fraction, so we want to make multiply each term by the denominator of the inside fraction. So it'll be 1 times x minus 3 over 1 over x minus 3 times x minus 3 minus 3 times x minus 3. And the x minus 3's will cancel on the bottom left. We can distribute the 1. I'll give us x minus 3. 1 minus, distribute the 3. Minus 3x plus 9. So this will be x minus 3 over 10 minus 3x. Okay, so then the domain restrictions, x not equal to, well, you can't get past this step here if x is 3, so x is not equal to 3. And in the final answer, x cannot be 10/3 because that will give us the denominator 0 there. Okay, so those were examples of composition of functions. We can also do other operations with functions. We can add two functions, f plus g of x. Just add the formulas. This is going to be 1 over x minus 3 plus x over x plus 2. You could get a common denominator, or you could just leave it like that. And the domain restrictions x not equal to negative 2, x not equal to 3. We can also subtract two functions. We can multiply two functions. I won't go over all of these operations, but division is maybe a little bit more challenging. F divided by g of x, so that's going to be f of x divided by g of x. So it's going to be 1 over x minus 3 divided by x over x plus 2. And the way you divide by fraction, you flip the bottom fraction, change it to multiplication. So 1 over x minus 3 times x plus 2 over x. And then you can multiply straight across. It would be x plus 2 over x minus 3 times x. Okay, so domain restrictions, you can't get past this step here if x is negative 2. So x is not equal to negative 2. And this step here, x cannot be 0. X not equal to 0, and x not equal to 3. Okay. G divided by f. So this is going to be g of x divided by f of x. So g of x is x over x plus 2 divided by 1 over x minus 3. Again, you want the way to divide by fraction, you flip it and change it to multiplication. So this is x over x plus 2 times x minus 3 over 1. Multiply straight across, x times x minus 3 over x plus 2. X cannot be negative 2. And you can't get past this step here if x is 3. So x is not equal to 3. Okay, so the inverse function. Now this notation, it's the same notation they use for multiplicative inverse, but this is a more general type of inverse. It might include a multiplicative inverse, but it also could include additive inverses, reverse order of operations, and so forth. It's a more general concept. That is the inverse function, not just a multiplicative inverse. So step 1, instead of f of x equal, we want to write y equals. And this is for x not equal to 3. Well, actually, we're more interested in what the y restriction on y is, but we'll get that in the process of getting the formula. Step 2, we switch x and y. So x is equal to 1 over y minus 3. And we want to solve this for y. We can multiply both sides by y minus 3. And on the left side, on the right side, the y minus 3's cancel. Left side will distribute. And we'll have xy minus 3x is equal to 1. And now we want to isolate the y. So we want to add 3x to both sides. And it'll give us xy is equal to 3x plus 1. And then divide both sides by x. And y is equal to 3x plus 1 over x. And this is for x not equal to 0. So the domain and range of the inverse function switch, so that tells us that the original function y would not be 0. You can also sort of, there's other ways of doing it. Okay, so the so y is, solving for y, we get y is equal to 3x plus 1 over x. X cannot be 0. That also tells us that in the original, for the original function, y was not equal to 0, because we're switching the roles of x and y here. And then the third step, instead of y equals, we'll write, use the inverse function notation. F inverse of x is equal to 3x plus 1 over x. And this is for x not equal to 0. Okay, so that's the inverse function, and the inverse function is also a one-to-one function. This step 2 actually tells us a one-to-one function, because we only got one formula for y. So the inverse of f inverse is the original function f of x. They're inverses of each other. Okay, so we can also find g inverse. There's maybe slightly more challenging here, because there's x appears in two places. So step 1, instead of g of x, we want to write equals. We want to write y equals. And then step 2, switch x and y. So x is equal to y over y plus 2, and we want to solve that for y. So multiply both sides by y plus 2 to get y out of the denominator. And on the right side, the y plus 2's will cancel, and the left side will distribute, and it'll give us xy plus 2x is equal to y. And we want y's to be on one side of the equation, so we can subtract xy from both sides to get y only on one side. I have 2x is equal to y minus xy. And then we have a common factor of y. 2x equals y times the quantity of 1 minus x. Divide both sides by 1 minus x. And we have 2x over 1 minus x is equal to y. And we can write that as, it's traditional, put whatever you're solving for on the left. So we can write that as y equals 2x over 1 minus x. And this is for x not equal to 1. Okay, and then step 3, we can use the inverse function notation. So g inverse of x is equal to 2x over 1 minus x for x not equal to 1. Okay. So that's another example. Describe f of x equal 1 over x minus 3 as a transformation of h of x equal 1 over x. We may recall that the shape here is hyperbola, with the center at 0, 0. Shape something like this. That's h of x. And so f of x is equal to h of x minus 3. So we're just changing the exponent. F of x is h of x minus 3. We're just replacing x by x minus 3. So that's going to shift it right 3. You might think it goes to the left because of the minus sign, but when you're adding and subtracting, multiplying things to the inputs, it has the opposite effect of what it looks like. If you're adding and subtracting or multiplying to the outputs, then it goes in the same direction that you would expect. And this one is a little bit trickier. Describe g of x as transformation of x of x. So we can we have to manipulate this a little bit. So g of x is x over x plus 2. We can write this as x plus 2 minus 2. That's the same thing. And then we can distribute the denominator. So this is going to be x plus 2 over x plus 2 minus 2 over x plus 2. So that's going to be 1 minus 2 over x plus 2. And we can write this as so h of x is 1 over x. So this is going to be 1 minus 2 h of x plus 2. Okay, so this is a shift left here. So we want to shift h of x left, and this is here we're multiplying h by a number, so this is stretch, vertical stretch. Stretches it vertically. This minus sign flips it across the x-axis, and this one here is shifts it up 1. So that's a more complicated transformation. So the h of x. Okay, the average rate of change of f of x from 0 to 2. So that's going to be f of 2 minus f of 0 over 2 minus 0. So this is the same thing we were doing with the rocket, except now it's in terms of a more generic function, no particular application. So this is 1 over 2 minus 3 minus 1 over 0 minus 3 over 2. So 2 minus 3 is negative 1. So this is going to be negative 1, and this will be minus a negative 1/3, so plus 1/3 divided by 2, negative 2/3 divided by 2, negative 1/3. So the average rate of change of f of x would be negative 1/3. That's the slope of the secant line. Average rate of change from 1 to 2. So that's going to be f of 2 minus f of 1 over 2 minus 1. F of 2, 1 over 2 minus 3. F of 1, 1 over 1 minus 3 over 2 minus 1 is 1. So this is going to be negative 1 minus a negative 2, so it would be plus 1/2. Divided by 1 doesn't do anything, so this is going to be negative 1/2. The difference quotient, okay, so the difference quotient, they don't really, they give you the difference quotient, but they don't really tell you what the importance of it, why it's important. So I'll do the difference quotient, but then we'll do, I'll take it a little bit further than what they take it in the book, because I think it helps to know how the stuff is used. Difference quotient is basically the slope of a line that touches the graph in two places. So it's the same thing we're doing up here with the average rate of change. It's the difference of y values divided by the difference of x values. So this is difference quotient is f of x plus h minus f of x over h. So this is going to be 1 over x plus h minus 3 minus 1 over x minus 3 all over h. And let's get a common denominator. Multiply top and bottom of each fraction by the denominator of the other fraction to get a common denominator. So we'll have x minus 3 over x plus h minus 3 minus x plus h minus 3 over, oh, this is times x minus 3. I left that off. X plus h minus 3 times x minus 3. That gives us a common denominator. So once we have a common denominator, then we can subtract. X minus 3 minus x minus 3 is going to cancel out. So we're just going to be left with the minus h when we do the subtraction. We'll have a minus h on top. Let's see. Oh, I left off over h. This whole thing is over h. Okay, so we'll have a minus h on top, and then x plus h minus 3, x minus 3, and this is over h. Okay, so the h on the bottom we can write as h over 1, and then so dividing by fraction is the same as multiplying by the reciprocal, so this is the same as times 1 over h. And then we can cancel the h's here, and that'll just give us minus 1 over or x plus h minus 3 times x minus 3. So that's the difference quotient, and the way the difference quotient is used, it can give you the instantaneous slope, the slope at each point on the curve, or in applications the instantaneous rate of change. So let's take it a little bit further. So the difference quotient when x is equal to 2, if we replace x by 2 here, that's going to be minus 1 over 2 plus h minus 3 times 2 minus 3. Just replacing x by 2. It's the difference quotient when x is 2. So this will be 2 minus 3 is negative 1. So it's negative 1 over h minus 1 and negative 1. So negative 1s will cancel. Negative 1 divided by negative 1 is 1. So this is just 1 over h minus 1. And then the instantaneous rate of change is going to be the limit as h goes to 0. So the point of this, as these points get closer, this is like y2 and y1, but as these points get closer and closer, the difference between the 2 points becomes 0. So we have to limit as h goes to 0 of 1 over h minus 1, 1 over 0 minus 1, which would be negative 1. So the instantaneous slope when x is equal to 2 would be negative 1. And in applications, the slope represents the rate of change. So that we saw from the example with the rocket, it would be the velocity, the rate of change in the height would be correspond to the velocity of the rocket. So it would give us the instantaneous velocity. So yeah, in the text they just give you ask for the difference, actually compute the difference quotient, but then they stop there, and they without really giving you an idea of why it's important. I took it a little bit further than what they took it in the book. And that concludes this presentation.